Thank you all very much for coming. I'm not sure whether you're here out of morbid curiosity about scheduling a defense on Friday the 13th, or I told Alex that you're here because you were interested in this talk. We had a long discussion about whether the advantages of a advantages with your committee about a Friday afternoon, having the committee tired and worn down, was better than the disadvantages of scheduling on Friday the 13th. So this is kind of a triumph of hope over fate. But anyway, we're very pleased today to have Alex present his dissertation defense. Alex received his bachelor's and master's degree in 1993 from University of Radio Engineering, Electronics, and Automation in Moscow. And after a year at the University of Delaware, he came to the physics department, the optical science department here at the University of New Mexico, where he's made some very nice studies and is presenting the latest chapter in the story on the properties of quantum dots. So with that, Alex, please.
The subject of my dissertation study Carrier-induced optical properties in 3-5 quantum confined laser nanostructures. I start my talk with the motivation for studying Carrier-induced optical properties in 3-5 quantum confined nanostructures. First of all, consider the difference in Carrier-induced optical properties between quantum dot nanostructures and conventional quantum wall lasers, which were fabricated at the same design. Next, I'll discuss engineering Carrier-induced optical properties in quantum confined engineering. The key parameter which were engineered was the orientation quantum confined nanostructure inside of the laser cavity with respect to the electric field of light, and quantum dot shape and chemical composition of barrier layers. I conclude my talk with modeling Carrier-induced optical properties in quantum dot media. When we talk about Carrier-induced optical properties, usually we having in mind change of the linear susceptibility with change of injection of the carriers, or change of the reduced Carrier-induced refractive index with respect of change of carriers. The real part of the index corresponding to the parameter which has the same name, Carrier-induced refractive index, but the imaginary part related to the material gain through the simple relationship. However, in real devices, we usually having business with model parameters, model gain and model Carrier-induced refractive index, which are connected to material parameters through the confinement factor. Probably the most universal and the most popular parameter for describing Carrier-induced optical properties in semiconductor materials is line-width enhancement factor. This factor shows how much change in Carrier-induced refractive index in the media when we change differential gain. It's a ratio of the differential index with the real part of the differential index to the imaginary part of the differential index taken with negative sign, and derivative, of course, with respect to the carrier density. Why do we buzz about why these parameters are important for optoelectronic devices? There are basically all semiconductor physics are influenced by the Carrier-induced optical properties. From the technology point of view, it's important for semiconductor lasers, laser amplifiers, and modulators. Such effects as laser line widths, laser noise, filamentation in high-power lasers, tube under direct modulation, and feedback effects are primarily interest to the technology. From the physical point of view, it's such effects like self-focusing and anti-gating. Why I'm particularly interested in carrier-induced optical properties in 3D quantum confined nanostructures, such as quantum dots? Well, the major reason is that ideal, once again, I would underline, ideal quantum dots should have unique characteristics, such as narrow and symmetrical gain, large differential gain, zero line width enhancement factor, and zero differential index. Just to go a little bit in detail, I'll try to compare, once again, ideal quantum well with ideal quantum dot. What they could expect from the point of view simple theory of linear susceptibility. Well, the major fundamental difference between quantum dot and quantum wells is, of course, density of states. In case of the quantum dots, the density of state is a step function. In case of the quantum dots, is a delta function. As a result, the density of states create very narrow and symmetrical should creates very narrow and symmetrical gain, which through the Kramer-Kroninger relationship should require to get refractive index change in such way, it's shown here by the broken line, that it crossing zero exactly at the gain peak. However, if we look at the same gain in case of the quantum well laser, the gain is broad and unsymmetric. And Kramer-Kroninger in this situation creates the difference, makes the index change, refractive index change, cross zero in the region of the gain was basically an absorption. So we can't get a refractive index change equal to zero in the range where we have lasing. And again, if we going bottom up, we get to the last graph which show line width enhancement factor as function of the photon energy. We see that the quantum dot, the delta pattern density of states make a line width enhancement comes through zero exactly at the gain peak. However, in quantum well, because of the unsymmetrical gain, the line width enhancement factor has a large positive value and will cross theoretically zero somewhere in far away in absorption. Once again, like ideally, we expect from one quantum dot have zero line width enhancement factor, zero differential index, and large differential gain. It's very such laser should be a unique laser because its properties should be comparable to the gas laser. And it's very interesting it's very important to justify that really it's important that it's possible to create such laser. However, the results which I showed you before were done for ideal quantum dots, which have homogeneous size and considered outside of the real device. In reality, the real quantum dot looks as shown here. This is how IFM pictures, and you can see that the size is definitely not uniform. The size is different, and if we grow them on atom-gallium arsenide substrate on indium phosphide substrate, in particular conditions, they can have very irregular form, elongated. So would we get ideal or close to ideal properties of the line width enhancement factor and carrier-induced refractive index, taking into account unidentiality of the real quantum dot structures. Also taking into account that these structures had to be inserted into the real device structure. At the time when this dissertation work started, there was no information that was known about quantum dash nanostructures. It's basically quantum dot which elongated in one direction and they're grown in a phosphide substrate. Also, there was no reports about spectral dependence of line-width enhancement factor for quantum dot nanostructures. So the primarily parameters of interest in the dissertation work will be line-width enhancement factor, differential index. It's derivative of the carrier-reduced refractive index with respect to the carrier density, and differential gain. This is derivative of the gain with respect to the carrier injection. Even so, there were some reports about quantum dot laser on the single lasing wavelengths. There was a very large variation of carrier-induced parameters. For example, here is a very important parameter such as differential gain, differential material gain. This parameter, the people who studied laser physics can be known as gain cross-section. So we can see that the value is varied from 2, basically 3 orders of magnitude. So, it's known that this parameter is fundamental constant, and usually it usually doesn't vary more than several times. If you look at the line-width enhancement factor, the reports also were quite different, from 2.7 to even negative value of minus 1.5. So this large variation in carrier-induced parameters requires the clarification of the subject. To find what is the difference between real quantum dot and quantum well structures, taking into account that there is a difference between real and ideal quantum dots. 2 laser structures were drawn. One quantum dot laser and quantum well laser, which has the same layer structure as quantum dot, but no quantum dots were drawn. So basically, the region with quantum dots in the well was replaced by the quantum well. These structures were processed in the rich waveguide laser, and the lasers which were fabricated had very good, relatively good performance. I would say pretty good performance. The threshold current density was 31 ampere per centimeter for cavity length 9 millimeter. It tells us that we're investigating one of the best quantum dot materials. To study, to obtain information about carrier-induced optical properties, we used so-called Haki-Paoli technique. Some people call it differently, but most known as Haki-Paoli technique. And it consists in measurements of amplified spontaneous emission spectra. By using Fourier transform infrared spectrometer, which allow to measure longitudinal longitudinal modes of the fabric raw cavity. Here on this graph are shown 3 amplified spontaneous emission spectra, which measure for 3 different injection current. As we increase current density from black curve to red and blue, we see that intensity of amplified spontaneous emission increasing. But at the same time, the peak of longitudinal modes shifting towards shorter wavelengths. This shift is the result of the change of carrier-induced refractive index in the active material. So by measuring this shift in longitudinal modes and depth of modulation of public raw cavity modes, we can easily obtain carrier-induced refractive index and model gain. by taking the difference of differential index and differential gain, we calculate line width enhancement factor. However, even so that this experiment looks quite straightforward, it's necessary to be careful because when we're measuring carrier-induced refractive index from the Fabric Bureau fringes sheet, basically we're measuring not only carrier-induced refractive index, but also change of the refractive index because of the change of the temperature of the region as we change the current. And the nature made it this way: the carrier-induced refractive index and thermal refractive index have different signs. So if we're not careful, these effects can be compensated, and we can easily get Nobel Prize result that the line width enhancement factor is zeros or even negative. So to avoid this problem, it's necessarily to get rid of the thermal effects. One way to do that is realize that the thermal part is a linear function of duty cycle. Duty cycle is the ratio of the pulse width to the period of the pulse. So by plotting the dependence of the carrier-induced refractive index with respect to the duty cycle, we can, by extrapolating it to the value of the zero duty cycle, we can obtain the real value of the carrier-induced refractive index, which is not affected by the thermal effects. Here are the results of model gain in quantum dot red curves and quantum well laser green curves for three current densities below threshold 0.6, 0.8, 0.9. We can easily observe that the spectral dependence of the model gain are different for quantum dot and for quantum well. Also, the band filling is quite interesting to point out here. It's quite different. Band filling, by band filling, I mean here the gain peak is shifting toward higher photon energy as we increase current density. However, in quantum dot, it's shifting. In quantum well, green curve, it's shifting linearly. But in quantum dot, it saturates. And plus, the rate of the rate of the band filling in quantum dot is substantially larger than quantum well, which tells us that the density of states in quantum dots are smaller. Here is we point out I show the normalized gain spectrum for quantum dot, red curve, and for quantum well, green curve. And immediately we see the reality. In reality, the quantum well spectrum should be narrow, but in reality, the quantum dot, in theory, the quantum dot spectrum should be narrower than quantum well, but in reality, the quantum dot spectrum is broader, and this is because of the inhomogeneous broadening as a result of quantum dot size fluctuation, which basically makes the spectrum broader. How about line width enhancement factor? Here's again green curve is line width enhancement factor, and in quantum well laser, and blue line width enhancement factor in quantum dot laser. We see that minimum values are practically the same. However, the spectral dependence are different. The dispersion of line width enhancement factor in quantum dot laser is substantially smaller. Plus, at the lasing wavelengths, the line width enhancement factor in quantum dot laser is approximately 1.5 times smaller. It's easy to realize it by looking at basically this difference in spectral dependence of line width enhancement factor comes from the difference of differential gain. We see that peak of the differential gain align basically with the peak of the differential gain in quantum dot laser. So we get the smallest possible line width enhancement factor at the lasing wavelength in case of the quantum dot laser. But in quantum well laser, the peak of the gain shifted 7 millieV from the peak of the differential gain. So we don't get the smallest line width enhancement factor at lasing wavelengths in quantum well laser. However, since we're comparing two different materials, quantum dots and quantum wells, we had to do a conversion from model parameters to material parameters to avoid influence of laser structure parameters such as confinement factor and different recombination rates. To do the conversion, we need to know carrier lifetime, optical mode volume in the laser cavity, and quantum and carrier recombination volume. And here we have a problem that carrier recombination volume are difficult to assess in quantum dot structure. That was actually a major reason why such a large fluctuation in material differential gain reported for quantum dot laser. However, we realize that differential parameters, such as differential index and differential gain, they basically don't depend on the carrier induced about carrier recombination volume. It cancels out. So by measuring carrier lifetime and calculating optical mode volume using standard waveguide method, this allows us to assess the material, differential material quantum dot parameters for the first time. Here are the results. If the model parameters in quantum dot laser are 6.5 times smaller than the same parameter in quantum well laser, material parameters are only 3 times smaller. The difference between model material parameters because of the difference in carrier lifetime, which is in 2-dimensional and 3-dimensionally confined materials. By summarizing the result of the comparison quantum dot and quantum well materials, we can make the following conclusion. The line-width enhancement factor is more than 0 in quantum dot lasers. However, there is a big difference between quantum dot and quantum well materials. Such like there is 6-time difference in, for example, the model differential index 6 times smaller in quantum dot lasers than quantum well, which can be very important for chirp application. Also, there is less dispersion in line-width enhancement factor and less dispersion in model gain. Also, we've been able to calculate material parameters from model parameters, and material parameters also in contrast to the theoretical prediction are actually 3 times smaller, both carrier induced refractive index and differential gain. However, is it possible to modify these parameters? Could we engineer the structure in such a way to make the line-width enhancement smaller and maybe get it to the theoretically possible value? Well, one of the ways to engineer is to change the orientation of the quantum confined structures with respect of the electric field of light. What we're trying to do here, it's known that the differential gain and gain are proportional to the dipole matrix element in quantum confined nanostructures. So is it possible for us to orient in the laser cavity quantum confined nanostructure in such a way to get the largest possible gain in differential gain? Well, just to give you a small reminder, like there is a big difference in dipole matrix element in quantum wells. For example, if electric field is perpendicular to the plane of the quantum well, basically there is no interband transition, and Because then if you get actually zero dipole matrix element, the gain will be practically zero. But if electric field is in the plane of the quantum well, then we get the largest possible gain in transition matrix element and consequently gain in differential gain. Could we do the same thing in quantum dot and quantum dash materials? Probably the most interesting object for investigation orientation dependence of Kerr-induced optical properties in concerning quantum confinement structures are quantum dashes, because there are all three spatial dimensions are different. Such structure was grown, was indium arsenide quantum dashes grown on indium phosphide substrate. They were elongated on 1-0 direction. And they were embedded in side of the quantum well and were grown cladding and high doping level to do the electrical injection. Again, this laser were processed and into the rich waveguide laser, and the same method was used to measure Kerr-induced optical properties. However, two lasers were made, one with dashes along the cavity axis. In this case, electric field is perpendicular to the dash axis, and dashes perpendicular to the cavity axis. In this case, the electric field along the quantum dash axis. And from the quantum wire theory, like I showed it on the previous slide, like from the dipole matrix element theory, the largest dipole matrix element should be like if quantum dashes behave as quantum wires, when the electric field should be along the longest dash side, then the dipole matrix will be the largest for lowest energy transition, which are conduction band heavy hole. So after we measured Kerr-induced refractive index change and gain using Hacking-Paoli technique, well, we immediately see the difference in model gain. When electric field along the longest dash side, so dash perpendicular to the cavity axis, the gain is larger than when dash is parallel to the cavity axis, and electric field is perpendicular to the dash axis. And also, besides the change in the gain amplitude, we see that there is a shift between gain depending on orientation. And if we look at this effect in more detail, this is basically band filling. We see how the gain peak is changing with current density. This gain shift is practically the same for all measured current densities. If we look at the derivative of the band filling with respect to the current density, we see that the derivative is the same for both orientation. And this is not surprising because the density of states are the same. It's the same structure, we just rotated it. But the difference are because of the difference in dipole matrix element with orientation. The same difference we see in differential gain is as we expected when it's possible to find orientation when differential gain will be the largest, and it happens that, as predicted series, the largest differential gain we get when electric field along the longest quantum dash side. But also, if we take the ratio of the differential gain for parallel and perpendicular orientation, we see that it's not a constant, but it's basically decreases this photon energy. And if we approximate the differential gain as ratio of dipole matrix element, which is a good approximation, if we assume that the homogeneous broadening is a delta function, then it basically tells us that there is not only difference in dipole matrix element amplitude, but also there is a difference in spectral dependence. How we try to get the largest differential gain by adjusting orientation. But what happens with carrier-induced refractive index? Unfortunately, as we increasing differential gain, we also increasing differential index, which is bad. And also for when electric field aligned along the longest dash size, the differential index will be the largest. Look at the amplitude. Oh, the amplitude is larger, -2 compared to 0.5 for parallel orientation. However, since we have a situation when, since Langmuir-Hassman factor is the ratio of the differential index to differential gain, we increase differential gain, but we also increase the differential index. So how about the ratio? Well, definitely there is a large difference in the ratio of these parameters. So there is, basically we can change Langmuir-Hassman factor by changing orientation of quantum dash in the laser cavity and change its spectral dependence. But the minimum value which you can get in quantum dash nanostructures only around 3.5. And if you look at the comparison of the carrier-induced optical properties in quantum dot, quantum dash, and quantum well, so you can consider it how the carrier-induced optical properties change with degree of the confinement. We see that, as I pointed out previously, that even so we increased differential gain compared with quantum well, we also increase the differential index. And the smallest Langmuir-Hassman factor, we got around 3.1. But in quantum dots, it was substantially smaller, 2.4. So if we want to engineer, if we want to continue, yeah, basically it's a summary of what I just said, so I don't want to repeat it. So if we want to continue engineering to get the smallest Langmuir-Hassman factor as possible, we have to go to quantum dots because it's the smallest Langmuir-Hassman factor we can get. And what kind of options we have? Since quantum dots are symmetrical, there is not much reason to rotate it in the cavity, but we can change dot size and we can change the composition of the surrounding quantum well. So three quantum dot structures were grown with different at different gross temperatures. Gross temperature allows us basically change the quantum dot size. As we decrease the gross temperature, the quantum dot size is decreasing, and at the same time, as you can see in this table, the density increases. Here is basically the IFM images. Basically, as we decrease temperature from 510 to 490, 470, 460, definitely see that quantum dot size is decreasing and density is increasing. So, would we get different carrier-induced optical properties by changing quantum dot size and quantum well composition? Here is the result. This is the spontaneous emission spectrums for lasers grown at different temperatures: 510, 490, 470, 460. Definitely, we can see that inhomogeneous broadening is changing from 67 millieV to 109. It basically increases with decrease of the gross temperature. Also, we're changing separation between ground state and first excited state. You see all this pictures in the same scale, so you can just visually observe that the spacing between ground state and first excited and first excited and second excited are changing. From ground state to first excited was able to change from 60 million to 74, but from the second from 41 to 116. However, what it does give when we measure the differential gain and differential index and line enhancement factor. Basically, as we change quantum dot size, line enhancement factor, we didn't observe a big change in line enhancement factor. But as we change quantum well, here was quantum well, deep quantum well, 15% of India. Sorry, this is shallow quantum well, 15% of India, compared to indium gallium arsenide quantum well with 20% of indium. So when we have a deeper quantum well, we basically be able to decrease line enhancement factor in two times. So summarizing this section, the line enhancement factor and differential gain can be engineered by controlling quantum dot dimension and especially quantum ball composition. But unfortunately, still the smallest line enhancement factor which we could get was only 1. It's not.
Look in the excited state. Just to ask.
Oh, you mean for the line enhancement?
Yeah.
Well, I've been able to see only in one laser. It was this shallow quantum well for first excited state. And it was approximately the same value as in the ground state.
This is the quantum well or the quantum dot?
Quantum dot. Quantum well and quantum dot, both measurements were done only for ground state. Lowest energy transitions. So basically, why we not be able to see the theoretically expected result? 0 line enhancement factor and 0 differential index. Well, since we've done probably what is possible, what we could do from the experimental point of view, we decided to go to the theory and see. Maybe we had to do more careful theory which takes into account unideality of the quantum dots, such as inhomogeneous broadening and excited states. Well, to do this, we had to calculate linear susceptibility, which allow us to calculate gain, Keren's diffractive index, and line enhancement factor by calculating differential gain and real part of the differential index and imaginary part. So the real part of the susceptibility can be calculated from the density matrix approach, including relaxation broadening. Also, we had to take into account here the plasma effect of free carriers in quantum well. Even so it's far away, the amount of carrier can be enough to take it into account. The same density matrix approach allows us to calculate the imaginary part of the real susceptibility and in similar way spontaneous emission. What we need to do is we need to find the occupation probabilities for electrons and holes in corresponding conduction valence band. And we need to know the density of states for the structure. Density of states, here is presented reduced density of states, is composed as combination of density of states of quantum dots for all. Here we're considering 3 states which were observed in spontaneous emission. This is this term. And second term is the density of states of the quantum well. Since we don't have a pure quantum dot structure, we have a quantum dot in quantum well. So we consider the whole region, quantum dots plus quantum well. To model the transition, we consider one electron states in conduction band and 3 hole states in valence band. we consider transitions which we see in spontaneous emission. Ground state, first excited, second excited, as transition from inhomogeneously broadened ground state in conduction band to inhomogeneously broadened ground whole state in valence band, and correspondingly to the first excited and second excited whole states, and transition from quantum well state in conduction band to the transition in quantum well in the valence band. The parameters of the transitions which we use in our model we take from the experimental data and the value of inhomogeneous broadening. To calculate occupation probability, we realize the following things. Since all our measurements are done at room temperature, we can have a break because we can consider equilibrium, quasi-equilibrium, and use Fermi statistic to calculate occupation probabilities. By using neutrality condition, by considering the number of electrons in on quantum dot states and quantum well states equal number of holes on quantum dot and quantum well state, by solving this integral equation, we can numerically calculate the Fermi level as function of the electron and hole densities for conduction in valence band. As we get that, we basically can get very intuitive picture how carriers occupy dot states and well states depending on the injection current or an injection carrier density. At the carriers, let's look first at this curve. This is shown number of carriers on quantum well state, green curve, and red is number of carriers in quantum dot states. As we increase carrier injection, at the beginning, at the small injection carriers, basically we can neglect carriers in quantum well. Mostly they occupy quantum dot, but as we get approximately to the carrier density twice the number of quantum dots density, basically quantum dots already filled up, and we start very rapidly fill up quantum well states. So what it tells us that it's large injection current densities, we should have very large leakage in quantum well. And here's the experiment which demonstrates this. Plus, don't pay attention to the green curve first. Just pay attention to the red curve. That's the optical power as function of the current density, basically spontaneous emission. We see that at the beginning here somewhere, it almost linearly increases. But as we increase current density, it saturates very rapidly. If we look at the quantum well of the same design, the same geometry, this is a green curve. Don't take association with that data. That green curve is completely different structure. It's just quantum well without quantum dot. We see that here spontaneous emission increases very rapidly with current. So we see that we don't get that radiative efficiency in quantum dot laser decreases very rapidly with current density, because basically after we saturate ground state, we start occupying not the excited states but quantum well, which basically because non-radiative high non-radiative recombination in quantum well, and because we had to have high injection, high inversion to get emission, we don't get high radiative efficiency.
So this is in two different structures?
Yeah, this is a quantum well laser. This is quantum.
Can you see this in just one dual structure as you increase, because then you have luminescence from the well?
It's very hard. I only on one structure been able to see lasing from quantum well, but no way I could get amplified spontaneous emission. So basically, it's almost impossible to answer the question.
But is this amplified spontaneous emission?
Yes.
Okay, well, I mean,
This is spontaneous emission.
Wait, is this out of the edge or the top?
It is out of the edge, and what I did, I made relatively short cavity, and I basically destroyed cavity from one side. So I removed feedback. So I know for sure that it's spontaneous emission.
But it's amplified.
I don't think it's amplified because feedback was reduced. So
Let's talk about it later.
probably, yeah, but partially maybe. So if we get this is the modeling result of the model gain, differential index, spontaneous emission, line mixing enhancement factor. First, we start with single theory. Just take single quantum dot state, neglect all quantum well state, and all excited states. Just single state, what we get? Well, we get high differential gain, 10 minus 14. We get 0 differential index at the gain peak. We get 0 line mixing enhancement factor. Everything is pretty conservative. So if we start model more complicated, if we add inhomogeneous broadening, if we add just high excited state without inhomogeneous broadening, what we get here is that even so the spectral dependence of the gain and spectral dependence of line mixing enhancement factor and differential gain and change. Right now we see we can resolve each state very clearly. Like it was hard to see, for example, in real spontaneous emission. However, again, even so, we took into account the excited states, we still can get zero line mixing enhancement factor at the near the gain peak and 0 differential index. So just only adding excited states doesn't explain us why we didn't get in experiment 0 line mixing enhancement factor. However, if we add 2 excited states in homogeneous broadening, first of all, we see that our spontaneous emission looks all practically the same shape as we get in experiment. So we see that here, line mixing enhancement factor is not non-zero on the gain peak, and the carrier-induced refractive index is also not 0 on the gain peak. This line corresponding to the 0. Here is 0 for carrier-induced refractive index, so it's far away from 0. Well, if we go even further and we add quantum well to the structure, so right now we consider all quantum dot states, all quantum well states versus homogeneous broadening. Basically, differential gain spontaneous emission doesn't change substantially, but the absolute value of the differential index and line mixing enhancement will increase because of the contribution from quantum well, because the real part of the Lorentzian is very slowly decaying, and it still influences the ground state quantum dot carrier-induced optical properties. Well, if we compare the parameters of interest, differential gain and differential index in quantum dot laser with experiment, here's the experiment, like blue, with numerical modeling of which include all quantum dot states, quantum well and homogeneous broadening, we get the differential gain 3.1 we made an experiment, plus minus 0.4. Theory gives 4.9. The differential index minus 0.7 plus minus 1. Here we get theory give minus 0.9. And line mixing enhancement factor 2.4 plus minus 6. Theory gives around 2. So the parameters are, if we took all things possible into account, we really get the theory and experiment agrees. However, if we will be not very careful and don't take into account quantum well, the differential gain doesn't change substantially, but definitely we don't properly calculate differential index. It becomes smaller because we don't take all contributions. We don't take contribution from quantum well. And also we see the line exponential factor is decreasing. And if we take what was considered in the early models when they consider ideal quantum dots, which are delta function, purely delta function density of states, non-homogeneous broadening, then we get huge differential gain and Laplace enhancement factor is 0. So the conclusion here is that it's important to consider quantum well state, consider all excited state, and consider homogeneous broadening to get accurate wave of the Kerr-induced optical properties. Well, here is kind of question which I asked myself. Well, how far away should we shift quantum dot and quantum well states to get properties, to get ideally predicted properties, such as zero line width enhancement factor and zero differential gain? Well, we had to move it to get exactly at the gain peak around 1 eV from, like, the separation should be from ground state to the first excited state. But to get it maybe somewhere, like to get length and zero distance the first ground state, maybe not necessarily on the gain, at the gain peak, it should be like I think at least 0.4 millieV. Well, here's contribution. The spectral dependence of the Kerr-induced optical properties and material properties such as differential gain, differential index, were measured for quantum dot and quantum dash structures. Polarization dependence of the Kerr-induced characteristic were measured in quantum dot and quantum dash structures. Modification of the quantum dot material parameters were demonstrated by engineering quantum dot shape, chemical composition of the barrier layers, and finally, a comprehensive model of the Kerr-induced optical properties was developed. I want to say thank you to my advisor, Kieran Malloy, for guidance and for the great help and for the patience as well. And I want to say very big thank you, Professor Gillisay. Really, he teach me a big deal about semiconductor lasers. Really, he's a great expert. And I want to say thank you, Luke Lester and Mansur Shekhbahai. And special thank you I want to say to Andreas Stins for growing my quantum dot, my wafers, and for teaching me how to grow. I wish I could learn more. And I want to say also a big thank you to Rongao Wang for fabricating quantum dash laser for me. It was basically, I didn't make quantum dash laser, it's basically Rongao Wang. He was the guy who made this wonderful laser. And I want to thank you to Tom DeRutter for collaboration in investigation of polarization property and quantum dot and quantum dash structures. Thank you.
Sure, Alex would be happy to answer any questions from the audience.
I've seen a few times you've been showing the gain spectra both on dots and ones which seem to be strange on the high photon energy side. You don't have an absorption there, it just stays at 0. At the beginning I thought it was just an illustration, but then you were showing the results, they also look the same. Some of the results were correct in terms of the again becoming absorption at high photon energies, but the original figure, the very beginning,
is it experimental?
The very beginning was kind of a schematic. Your very first illustration of gain spectra of 0.1 and 0.0.
Like slide number 2.
Yeah, 2 or 3.
Drew by hand.
It was, I noticed that.
Yeah, and that one was correct, by the way. That was going down from low zero. But your schematic illustration, you see, it doesn't look like flat. Well, you never have any absorption before, no matter how big photon energy.
Oh yeah, it's true. Here I consider it basically, in ideal case I consider only ground state, and it's true. I a little bit idealized picture here, just kind of. It's yeah, I draw it back basically.
But then, then of course you showed the calculations the component was which do go below zero, so that's fine. But the component don't, it never happens. You still have this.
It's a compilation experiment.
You still have your calculated on dot gain spectra that never show any absorption. That means you never kick out the electron out of ionization from the dot.
No, actually I did.
Never absorption.
Just if I understand you correctly, just be sure that you're talking about the same thing. There's an absorption, right? Then absorption is decreasing.
So you're saying the quantum wells are transparent to light or sufficiently high photon energy? No ionization
if we have a high injection current, yeah, like an experiment, we've seen that we can get lasing on the second and third state. So definitely that means that we get basically transparent there.
Well, and what happens at what's happening at 1.4 eV?
Yeah.
Oh, here's already quantum well, but here we didn't take into account quantum well, so we need to go to the next stage. And here I just cut it out at 1.2, but if we should go, I think here, right? That's I basically go to 3, and you see there's a quantum well at absorption here. Right, this is quantum dot ground state, this is quantum dot excited state, there's absorption here, and here's quantum well, there's absorption. So basically over there, I just didn't show the region where was absorption.
So if the density of states is a delta function, does it absorb energy above the transition?
If the density of states is delta function, would be absorb energy.
Absorb, would there be absorption above if the light is above the transition?
So let's just understand you. I mean, we have energy which is equal to the transition energy.
Above the transition. What's the absorption coefficient?
Wow, I don't get it.
Yes, 0.
But that's a idealization of the real situation.
Yeah.
But because in an atom you could argue the same, that you have delta function density of states on a certain level, and yeah, you can ionize into vacuum, and then you
If there's a continuum there.
yeah, there's a continuum of states which you are neglecting.
No, I
It exists.
well, quantum
Well,
well.
there isn't a continuum, it's a quantum
Well,
dot.
Quantum well, there's a continuum. Basically.
if there is an isolated quantum dot, and you eliminate that with the photon that would ionize the electron, it is zero.
Right, but I just
Photoelectron.
I just kind of don't see.
You didn't add a continuum. There is no continuum in your quantum.
In your idealized know there is no continuum of states above your confined levels.
Oh, right. Yeah, of course. I just basically stopped. Yeah, after my quantum. Yeah, that's true. After I didn't. Yeah, that's true. That's I probably should have been. No, actually, I have a continuum. Yeah, because actually my density of states is I took into account as Gaussian. So basically, there is density of state, but they not occupied, and the density of state is decreasing. So basically, when I go far away from the sort of excited states, so for example, somewhere between quantum dot and quantum well, basically there is no states. There is no state, there is no absorption. Like at least in the model which I used. Right.
Can you comment on its realisticness? Realism?
Well, I choose, of course, I choose the simplest model which could explain my experimental data.
Yeah, your data will not be in the type
This
of
model is most close to reality among all individuals.
Surely you have no interest in looking at hyperdynamics because that's not.
Yeah, I'm investigated on that.
I have a question. You assume that you just had one electronic state in your term.